Question number 4. If we take a look at question number 4, it says a sample of metal M is vaporized and injected into a mass spectrometer. The mass spectrum tells us that 60.10% of the metal is present as M69 and 39.90% is present as M71. The mass values for M69 and M71 are 68.93 AMU and 70.92 AMU respectively. What is the average atomic mass for sample M? Well, this is straight up, do you know the formula? Can you plug the things into the formula and solve? Our formula for a weighted average, how do you spell weighted? Weighted average is equal to the mass of isotope 1 times the percent abundance of isotope 1. That's a parentheses. Then you add to that the mass of isotope 2 times the percent abundance of isotope 2. And if we had a sample with more than 2 isotopes, it would just keep going. But since we only have 2, we're just going to stop at this point. Next, all we need to do is plug and chug here. We take a look at the first isotope, which has a mass of 68.93 AMU. Its percent abundance is 60.10%. Don't forget, as we work with these percentages, we need to move our decimal 2 places to the left. So we're going to multiply that by 0.6010. And then we'll add to that the product of the mass of the second isotope, which is 70.92 AMU. 70.92 AMU times its percent abundance, which we are told is 39.90%. Again, we'll move our decimal point 2 places to the left to get 0.3990. Then it's just a matter of solving, busting out our calculator to solve, and when we do that, our product here is 41.4269. I'm going to put a little reminder here for sig figs. And when we take the product of those second numbers, we get 28.2971. Also a little reminder for sig figs there. And then when we solve this, add this all together, we get 69.7240 AMU. Or using sig figs, 69.72 AMU. Final answer. As you think back and ask yourself, does this answer make sense? Yes, it does. Here's why. Generally, your weighted average is going to be closest to the most abundant isotope. As we take a look at the most abundant isotope, our most abundant isotope is M69, and this is a little bit closer to 69 than it is to the isotope M71. So, feeling good. Final problem of the day. It's a doozy. Number 5. The element indium exists naturally as 2 isotopes. Indium-113 has a mass of 112.9043 AMU, and indium-115 has a mass of 114.9041 AMU. The average atomic mass of indium is 114.82 AMU. Calculate the percent relative abundance of the 2 isotopes. So, very similar problem to the last one, sort of, in as much as we are going to use the same formula as we did in problem number 4. So I'm going to come back here and grab this formula. So that we can use it here in problem number 5. The difference with this problem is that we're given the weighted average. We're told that the weighted average of indium is 114.82 AMU. What we're asked to find are the relative abundances or percent abundances of each of them. So we're going to be looking for these 2 things. Now we can tell that they're not the same number because the weighted average isn't halfway between the smallest and these two isotopes. So how are we going to figure out what they are? Well, we're going to use the magic of algebra to help us solve this problem. First, we need to recognize that the sum of the percent abundances of all the isotopes has to add up to 100%, or one whole. All of the isotopes together has to equal this. So if I had X to represent the percent abundance of isotope 1, and we'll do it in orange here, plus Y to represent percent abundance of isotope 2. That is great, but we'll have two variables in our problem, and it'll be very difficult for us to solve, / impossible. So to solve that dilemma, we're going to solve this equation for Y. So let's subtract X, and that will give us 1 minus X equals Y. So how can we use this information to help us solve? Well, if we set the percent abundance of our first isotope equal to X, right, and our percent abundance of the second isotope equal to 1 minus X, then it just becomes a matter of using our awesome algebra skills to solve this problem. So now let's plug them in and jug. Our weighted average here is 114.82 AMU. The mass of our first isotope indium-113, has a mass of 112.9043 mu. AMU. Times its percent abundance, which we said was X, because we don't know. We're going to add to that the mass of the second isotope, in this case indium-115, which has a mass of 114.9041 AMU. 114.9041 AMU. Times its percent abundance, which is 1 minus X. Whoa. Okay, so now it's straight up algebra time. We're just going to simplify all of this. Crazy. 112.9043x. Just going to multiply that number by x. I'm going to drop my units here to make this a little easier to understand. Plus, we're going to do some distribution. 114.9041 times 1 is 114.9041 minus 114.9041 x. Woo! 82 on this side. So we're going to combine some like terms here. We're going to subtract the two x terms from one another. So we're going to get negative 1.9998x. So I just subtracted this from, well, I subtracted 114.9 from the 112.9043x. Plus our 114.9041. 114.82. Getting close. Then to solve for x, we're going to subtract 114.9041 from each side. 114.9041. Man, that 4. Which will leave us with negative 0.841 on our left-hand side of the equation and negative 1.9998 x on the right-hand side. Then we just divide each side by negative 1.9998. Boom, sucker. 1.9998. Woo. Therefore, x is equal to 0.0421. Now, what the heck was x even supposed to represent? We're going to come up here really quick. If you remember, x represents our percent abundance for that initial isotope. Oops, that initial isotope. So if we convert this decimal into a percentage, it is equal to 4.21%, just by moving your decimal 2 places to the right there, which is our percent abundance of isotope 1, which was our percent abundance of indium-113. Boom. Okay, now to solve for the second percent abundance, all we need to do is plug x back into our formula for y. Y equals, remember, 1 minus x. So 1 minus 0.0421, which means that y is equal to 0.958. Or if we convert that to a percentage, it's going to equal 95.8%, which is our percent abundance of indium-115. Woo! Done.